Good morning, everyone. Thank you for being with me. Today, I'm going to talk about the Higgs boson in particle physics. The topic here reads search for a vector like a quark in two-photon final state. So basically, vector like a quark is a new particle related to the Higgs boson. It sounds complicated, indeed it is, but let me talk about it starting with an analogy. Imagine you are on top of a snowy slope and just for fun, you push down a snowball. The snowball begins to roll down and becomes larger and larger. By the time it reaches the bottom of the hill, it ends up being much heavier than when it started. Sounds reasonable, right? This is also what theorists predict too. So suppose that the mass, the weight of the snowball, we say that the mass is about 1 unit. Then we are curious about how is its experimental value. And surprisingly, it turns out that it is very small. It's like a 0.000, oh my god, so small. So how can that be? Maybe there is something we don't know about this scenario. So various theories make some prediction about that. Maybe on the snowy slope, there exist snow supporting structures like snow fans. These snow fences can stabilize the snow field, and when the snowball goes through it, somehow it crashes and becomes smaller and go again. So these snow fans will reset the size of the snowball. So at the bottom of the hill, the snowballs end up being very small. So this seems to be explainable. And in particle physics, these snow fans correspond to a new particle called vector like a quark. Vector like a quark is one solution to explain the so-called hierarchy problem of the Higgs mass. So in my study, our purpose is to look for these new particles. But what's the benefit of doing this kind of study related to the Higgs boson? So first of all, the Higgs boson actually accounts for the mass of fundamental particles. So basically, everything in the world is made of atoms. And on the right-hand side, as you can see, this is the structure of an atom. And without the Higgs boson, the electrons surrounding the nuclei, the electron will become massless and escape from the atom. So atom will fall apart. If atom fall apart, then basically everything cannot form because the atoms will repulse to each other, so anything cannot form. So Higgs boson is crucial to the world. Second, the Higgs boson has been driving the advancement of the technologies. So there are 3 examples. The first example is the World Wide Web, or W, the web. So this web emerges for the purpose of the nuclear study. And especially it happens at CERN. And CERN has put it as an open source so everyone can use it. Now it has become part of our daily life. The second example is hadron therapy, because we have a mature particle accelerator technology. And this is a transferable knowledge, so we can put it in medicine. And in medicine, we can use this kind of hadron therapy to treat the cancer tumor. So we can treat the cancer cells more effectively. The third example is is related to the algorithm developed in our study. It can apply to industry, like we can develop self-driving car. So the algorithm can fast analyze if there is accident coming to happen and prevent the accident. So these are all the advancement technology we have, thanks to the Higgs boson. Third, Higgs boson opens a portal to new physics. So this is what physicists care about. There are still many scientific questions remains to we need to answer to. And we are just like in the edge of discovery in 15th century. And the Higgs boson is the key toward this unknown cushion to an unknown land that no man has been to before. So it is important. And here is the agenda. So I'm going to talk about the CMS detector, a particle detector we are used to take data. Then you will get a sense of the, how a proton-proton collision event looks like. Then you will also know that how we differentiate signal from the background, followed by result and summary. So this is a cross-section view of the CMS of the compact muon solenoid detector. So it looks very complex. And if you count the floor, you will notice that, oh my God, the height of the detector supersedes the 5th floor. So it is gigantic. Although it looks very complex, but the purpose is very simple. It acts simply like a scientific camera. And surely it is not made by Sony. It is a detector collaborated by many countries and institutes all over the world. So this is our everyone, the achievement of humanity, I would say so. Yeah, so how does the photos look like with this scientific camera? So in the event display, we would have a figure like this. So at the center, there is many particle goes out. So you will see many tracks from it. And then particularly in this photo, you see there are 2 green bars. They corresponding to 2 photons in our analysis, which is important. And another figure goes like this. Look at this. This is cute and beautiful, isn't it? So we can display also the place of the 2 photons here as well. Then how is the signal in our study looks like? So we used to use this kind of diagram. This is the so-called Feynman diagram. So starting from left, there is a particle comes in. This particle is the vector-like quark, the particle we are looking for. Then at some point, it will decay to 2 particles, like marks as T and H. These particles will split and fall apart further. And what we care about is the particles at the ends of the diagram. So these particles are the so-called final state particles, and they are expected to appear in the scientific camera, as we just mentioned before. Yeah, so it may still be abstract to you, but let's just take the signal as this salmon sushi. So imagine you go to a sushi shop, and suppose you are a big fan for salmon. So your top priority is definitely to look for this salmon sushi. However, in our scenario, this kind of sushi is very rare. Most of the time, you will find sushi like this, very common and boring. So our task is to look for this yummy sushi from the boring sushi. However, there are actually 200,000 pre-selected photos to be analyzed. How can a human do this by his naked eyes? That's impossible. So we need an AI to help us for the analysis. This AI can help, if we input a photo to it, it can help differentiate whether it looks like a yummy sushi or it is a boring sushi. And particularly, the algorithm we are using is the so-called boosted decision tree (BDT) algorithm. This algorithm will give a score to the photo. For example, if the photo get a grade like 87%, then we tend to believe that it is very likely a signal. If it receives a grade of 10%, then we tend to believe that this is a background event. So with this algorithm, we can categorize or order the photos according to the grade. Then we will get a distribution like this in histograms. So on the right-hand side, this is where the signal will populate it. On the other end, those are background. So with this algorithm, we can separate these two events in two ends. And if we transform this into a distribution, it will look like this. The background is basically the noise. It can distribute it like this, while the signal populated on the right-hand side, as we just discussed. Then there is an intersection point, so we can set a threshold over there. Then we throw away the unwanted background event and keep the remaining part. Then we can use a figure of merit called signal to noise ratio. That is basically we take the area on the curve and take the ratio of it. So this is a good estimator for us to optimize the threshold. So let's go into the real stuff. So this is what the real distribution we have in our analysis. It looks much complicated than what I just shown, but the concept is basically the same. So in this histograms, the black dot represent the observed event, while the red and the blue represent similarity signals, and all the others are background events that are basically composed of many different kinds. And if you check the lower pad, which shows the ratio of data over Monte Carlo, and you see most of the dot goes along with the ratio 1. That means that our simulation describe the data very well. So the result is our method is very convincing and believable. Then similarly, we optimize the threshold and keep the signal enriched region. Then we take those events for statistical analysis, so that we can check the result. So here shows a distribution of diphoton invariant mass, and yeah, it looks again seems to be complicated, but we can decompose it step by step. So first, let's look at the sideband. So since this is a mass spectrum, so for the event on the left-hand side, those events correspond to a low mass. So you can treat it as like a sushi, but in small size. On the other hand, for the event at the right-hand side, this corresponding to high mass. So it is basically a large sushi. Neither of them is delicious. What we really want is something in the middle, corresponding to salmon sushi. And this salmon sushi basically forms a peak over layer. So we basically tell whether we can see new particles from this region. However, this is not enough. What we really want is this premium salmon sushi. Yeah, so this is much yummy than the common salmon sushi. And however, this is very rare in a sushi shop. In our study, in the end, we haven't found any of these premium sushi yet. But does that mean all our efforts are in vain? No, we still get some valuable information. So from our data, we can say that we have analyzed so many events, but we still haven't find it. So the appearance rate of this sushi is very small. So this basically is the concept of upper limit. We set upper limit over the new particle we are looking for. And since the upper limit depends on some parameters in our study, so we make it as a spectrum. So this plot shows the distribution of upper limit of the new particles. And from the figure, you can see there is a solid black line. And above these solid black lines, basically the region above is excluded. Okay, I'm not going to talk more about it, but the message here is that with this figure, physicists will get a better idea of where the new particles will be if the new particles still exist. So we have reached an end. Let me summarize. Today we have talked about the Higgs mass problem and also present the search for the new particles. And actually this is the first search for the vector-like quark in diphoton channel at the Large Hadron Collider. We utilize a machine learning algorithm in our study, and we report our result through upper limit. Last but not least, all of these kind of Higgs boson related studies basically put us sailing toward unknown. One day, maybe we will find an unknown land that no man has reached before. Thank you.